All right, so let's see here. We're starting off with nucleophilic addition reactions, and we're going to cover a couple of, kind of basics here about nucleophilic additions at carbonyls, and then we're going to get into some more specific reactions. So you should know that a carbonyl is electrophilic, right? If you just draw a carbonyl, and of course we find the carbonyl in an aldehyde or a ketone, and that's the topic of the chapter. Right? If you just look at a carbonyl, we know that there's a dipole between the carbon and the oxygen, and therefore we know that the carbon is partially positive, which means it is an electrophile, right? It's susceptible to nucleophilic attack. And let me ask you a question then. If I was to protonate the oxygen, so let's say I did a proton transfer onto the oxygen so that it had a positive charge like this. How is that going to affect this carbon? Is it going to be more electrophilic or less electrophilic than it was before it was protonated? It's going to be way more electrophilic, okay? It's going to be much, much more electrophilic, right? And the reason for that is if you draw the resonance structure here, right, it's much, 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 much more electrophilic, right? If you draw the resonance structure here, then you end up with this, where you have a positive charge on the carbon. So you can see that you have a full-on positive charge on the carbon. If you have just a regular old ketone like this, yes, you can draw a resonance form like this, right? But then that positive charge is balanced out by a negative charge on the oxygen, right? So in this one, we have just a complete total positive charge partially on that carbon, whereas in the other one, it's going to be balanced out by a negative charge. Does that make sense now? Okay, so you could do it like this. This carbon is mildly electrophilic. This carbon is hugely electrophilic, okay? It is a mega electrophile. So that thing is super susceptible to nucleophilic attack. So we went over the whole idea of resonance, and we went over why an oxonium, so this is more electrophilic than just a regular old carbonyl. And so another thing you should know about a carbonyl is that when you look at that carbonyl, right, you look at the carbon is sp2 hybridized, therefore it is trigonal planar, right? It's completely flat. And so that means it's susceptible to nucleophilic attack from either face of the molecule. It could attack from the top or it could attack from the bottom, and then we end up with something that's tetrahedral. Well, it says here that aldehydes are generally more reactive towards nucleophiles than ketones. There's two good reasons for that. The first of which I bet you could have guessed immediately, and that is the steric effect, right? If you just compare, you have a ketone versus an aldehyde. Well, with an aldehyde on one of the sides, you only have a little proton. And so a nucleophile is going to attack that before it would attack a ketone. Oops, let me just draw it like this, right? A nucleophile is going to attack there first before it would attack a ketone. The second reason is an electronic effect, which you might not have guessed. But in with a ketone, we have two R groups donating electron density towards the carbon to kind of diminish the partial positive charge. Whereas in an aldehyde, we only have one R group that's able to do that. And so the R group, the carbonyl carbon in an aldehyde is more partially positive. So therefore, it's more attracted to a nucleophile or more susceptible to nucleophilic attack. Now, some nucleophiles require acidic conditions, whereas others, they don't. They require basic conditions. And one that we've seen already where you would use basic conditions would be the Grignard reaction, right? If you take this compound, this ketone, and you treat it with methyl magnesium bromide, so we could write out the Lewis structure, which looks like this, right? We know that our methyl group, or our methyl anion, is going to attack here. And so in the second step, we're going to treat that with water or aqueous acid, and that's going to give us the tertiary alcohol here. So if you use a strong nucleophile, like a Grignard, that means the reaction is probably going to be under basic conditions, right? So that would be a hydride or a Grignard or something of that ilk. So under basic conditions, all nucleophiles react with carbonyls by the same old mechanism over and over and over. And so anytime I draw a mechanism in this chapter, you can assume that you need to know it unless I tell you no. Okay, and so you definitely need to know this mechanism here. We take a basic nucleophile, so something that's a good nucleophile and a strong base. We draw our nucleophilic attack, and then we do a proton transfer in the end to make an alcohol. Keep in mind that we have a negatively charged intermediate that we end up forming here, and so that's why you have to treat it with an acid at the end, and it could be water, okay, it could be H2O, or it could be hydronium, one or the other. All right, so it says here that aldehydes and ketones can also react with a variety of weaker nucleophiles if they're protonated first, right? Under acidic conditions, we can protonate the carbonyl oxygen first to go from a good electrophile, we'll put here good electrophile, to an excellent electrophile, right? And I just went over the reasons why when you protonate it to form the oxonium, right? This is what we call an oxonium. You end up with something that's a much stronger electrophile, and so it's now even more susceptible to nucleophilic attack. You don't even need a strong nucleophile in this case. And so it can even be attacked by a weak nucleophile, and an example of that would be something like an alcohol or water could even attack that. So again, if you want to react a carbonyl with a weak nucleophile, it's got to be protonated first, right? Because we have a very powerful electrophile when we protonate. Okay, so hopefully we all will remember that now. When you have a carbonyl, right? If I was to try this with you one more time before we move on, if we had just a regular old carbonyl versus an oxonium ion, which one of these is going to be a more powerful electrophile? The one in black or the one in blue? Exactly, okay? So stronger electrophile. All right, and I want you to keep that in mind because it's going to come up over and over and over in this chapter. So it says, when a nucleophile attacks a carbonyl group, the equilibrium will depend on the ability of the nucleophile to function as a leaving group. Now, if you were to protonate a carbonyl with HCl and then chloride comes in as a nucleophile, well, you can make this species here, but remember that chloride is a really good leaving group. It's one of the best leaving groups, right? It's the conjugate base of hydrochloric acid, and so it's an excellent leaving group. And so it says here the equilibrium actually favors the ketone in this case. So this reaction is kind of useless. And so we're going to look at ways to make the equilibrium shift in the direction that we want to. And I'll explain to you how to do that in a little bit. But before we get into that, let's go over all the different types of nucleophiles that we're going to look at. We're going to look at oxygen nucleophiles. And you see that none of these are strong nucleophiles. And so they're going to have to react with, protonated carbonyls, right? They're going to have to react with oxoniums because, again, they're so weak. So if you put, the lone pair in here, then you can get a nucleophilic attack like this, but that's the only way it's going to work. The same thing with a sulfur nucleophile or a nitrogen nucleophile. These are weak nucleophiles. Then we get into hydrogen nucleophiles. These are a little bit stronger, so lithium aluminum hydride, sodium borohydride. And then at the end, we're going to talk more about Grignard chemistry. So this is a Grignard reagent. This one here is a cyanide, of course. I think you know that one. And then the last one here is one of the main reactions we're going to talk about in this chapter. It's called the Wittig reaction. Obviously, this person is German, so we don't call it the Wittig. We call it the Wittig, right? Anyhow, again, Wittig won a Nobel Prize because he learned a way to make carbon-carbon bond. Okay, so let's get into the whole idea of oxygen being a nucleophile. And like I said, water is not a strong nucleophile. It's a weak nucleophile. And if you take a ketone like acetone, that's what this is here, acetone, and you put it in water, it's actually in equilibrium with a hydrate. And so a hydrate is a new functional group. Functional group. And this is a functional group you need to know. The hydrate is one that's important to you. It says here, generally speaking, the equilibrium doesn't favor the formation of the hydrate unless you have a really simple aldehyde. Like if you have, formaldehyde, in that case, it will favor the hydrate, but normally It doesn't, okay? However, the rate of the reaction is slow unless you spruce it up with some acid or base. And so if you do it in basic conditions to try to make a hydrate, well, the hydroxide is going to function as the nucleophile, and then you would do a proton transfer with water. So this is an important mechanism, base-catalyzed hydration. Star is so bad that the iPad doesn't even recognize it. There we go. All right, so that would be an important mechanism. Under acidic conditions, it's a little different, right? The first step is the protonation to make the oxonium. So you use your acid to do that. And then water can come in and react as a nucleophile here. And then we do another proton transfer at the end, and we make our hydrate. And of course, when water picks up this proton at the end, you end up recycling, and remaking your hydronium. So you just reproduce it over and over and over. Now, keep in mind the following when drawing mechanisms. This is not from the brain of Mr. Dion, this part here. This is from the brain of Dr. Klein, the author of our textbook. I was never taught this as a student, and if I was making up the notes, I probably wouldn't even think to bring this up because I don't see students do this a lot, at least not much, at least not that I notice it on quizzes or anything. However, he is a really good teacher, so I'm going to take his advice here. And basically all he's saying is this: if you're in acidic conditions, okay, you cannot draw any strong bases in there. So if I give you sulfuric acid or toluene sulfonic acid or hydronium as a catalyst, you should not be drawing hydroxides in there. Okay, that would be a big, big no-no. The converse is also true. If you're in basic conditions, then don't be drawing a bunch of hydroniums when you're in basic conditions because they're not going to exist in there, right? So acidic conditions, you have to remain consistent with those. In basic conditions, you must remain consistent with those too. Give me a thumbs up if you follow me on that idea. We have to be consistent with the conditions. Okay, and I realize I'm lecturing a lot. There's not a whole lot of questions at the moment. It's just a lot of content that we're going into. So let's take a look at a brand new functional group. Check this out. Instead of using water as your nucleophile to make a hydrate, we can take a carbonyl, like an aldehyde or a ketone, and treat it with an alcohol, namely two equivalents of an alcohol. So this is some kind of alcohol. There's two equivalents of it. This is our acid catalyst, so acid catalyst. And we end up making a new functional group called an acetal. You definitely need to know what an acetal is, okay? So an acetal, if you look at it very carefully, it's kind of like you have carbon, oxygen, carbon, and then carbon, oxygen, carbon again. It's like you've got two ethers attached to the same carbon, but we call it an acetal. All right, give me a thumbs up if you see the acetal. So it's kind of like two ethers attached to this carbon here. Okay, it's a very important functional group. We're going to talk about it a lot for the next, a little bit here. So I want to make sure that you're aware of that. All right, so what kind of acid do we use for a catalyst here? Well, what we normally use is either sulfuric acid, okay? So either H2SO4, this guy here, or we use toluene sulfonic acid, and the abbreviation we use is TSOH. If you're wondering, why wouldn't you just leave it as sulfuric acid? Why would you include this thing? It's because what I have in the red circle, the toluene sulfonic acid, it's also called tosic acid. Tosic acid is a shorthand for it. Or it's also called PTSA, toluene sulfonic. Yeah, it's got a lot of names. Anyhow, I digress. It's a solid at room temperature. So it's really easy to work with solids, especially if it's such a strong acid. You can recrystallize it really easily. And it's just, one of the favorites of chemists. So what does it look like when we form our acetal? So what we're covering right now is this mechanism, okay? The mechanism of this reaction. And the thing is that what they're not showing you here is you go from the ketone to the acetal, there's an intermediate that's formed that's called a hemiacetal. So you can kind of look at this big, long mechanism, which you do need to know, in sort of two steps, okay, or two major parts. The first part is the formation of the hemiacetal. That's this part here. And then in the next part, you're taking the hemiacetal and you're converting it into the acetal. So those are kind of the two main portions of the mechanism. Now let's study the hemiacetal quickly. Notice that the hemiacetal, on this carbon, you have like an ether here, carbon, oxygen, carbon, but then you have an alcohol. So it's kind of like you have an alcohol and an ether on the same carbon, right? An acetal was like two ethers. A hemiacetal is like an alcohol and an ether. So let's take a look at the reaction. Now we know that an alcohol is not a strong nucleophile. And we're doing this reaction in acid, right? We're talking about doing this reaction in acid. And so what's going to happen first is our acid is going to protonate the carbonyl to make the oxonium, which is an excellent electrophile. And now a molecule of the alcohol can come in and do a nucleophilic attack, and we form this tetrahedral intermediate here. So now remember that we're trying to get to the acetal down here. That's where we're trying to get to. So what are we going to have to do? We're going to have to lose this group. But we can't lose an OH minus because you can't have a basic molecule in acidic conditions. So we're going to have to do two successive proton transfers. One to remove this proton here from this oxonium. And then once you remove it, you're going to protonate where the hydroxyl is to make a good leaving group, right? Because water is a good leaving group. It's the conjugate base of hydronium. So now when the water leaves, you end up forming another type of oxonium. This is not a protonated oxonium, but an alkylated oxonium. And so now another molecule of an alcohol can come in. You do a proton transfer at the end, and there you go. There's your acetal. Done, just like that. Okay, so this is a mechanism that you need to know, and this is a mechanism we are going to practice as a group. I'm just checking to make sure I have an example of it. Yeah, I do in a few slides. We'll go over an example of this, but I want to address something with you is, look, what we're mixing here is we're mixing the carbonyl compound, right? The acid catalysts. Okay, maybe I should put this over here a little bit more, okay? All right, then we have our alcohol. So we have two equivalents of our alcohol like this. Okay, and then what are we making in the end? We're making our acetal. And keep in mind that we're also going to liberate water, okay? And that water molecule is liberated in the second half of the mechanism. So I want to address what's HA plus. Sometimes this will confuse students, so I don't have a lot of space here. So let me just go over to a blank space here for a second, and we'll talk about this. Son of a gun, so just bear with me here. Okay, so if you're wondering what's HA plus, when it writes here, HA plus, what is that? Well, keep in mind we're taking a strong acid and mixing it with an alcohol. So if we have an alcohol plus a strong acid like sulfuric acid, we're going to have an equilibrium between this and the protonated form of the alcohol, all right, and the conjugate base of sulfuric acid, like this. So remember, sulfuric acid has a pKa that's about -9, and the protonated form of water or an alcohol is going to have a pKa of around -2. So the equilibrium is going to lie to the side of the weaker acid, right? So our equilibrium is going to lie to this side. So this is our HA plus. It's the protonated form of the alcohol, but we just usually abbreviate it like this. Right, so this would be our H, and then all the rest of it here, this would be the A plus portion here. So it's just the conjugate acid of the alcohol. Give me a thumbs up if you follow me on this. Very important, acid-base equilibrium. This goes all the way back to chapter 3 of Organic Chemistry 1. Okay, I just wanted to address that because I've taught the class long enough to know that sometimes students are, what was that again? You know, and I don't blame you one bit. You're allowed to ask a question, right? This is the land of the free. So acetal formation is an equilibrating process. And it says here that for most simple aldehydes, yeah, the acetal is favored. However, if you have a ketone, the acetal is not favored in that case. And so what do we do? How do we drive the reaction forward? The way that we do that is we take advantage of Le Chatelier's principle and we remove the water from the reaction. Now, in the book, it says using a special distillation technique. It's called a Dean Stark trap is the name of the trap. So you can Google it if you want. It's called Dean Stark trap. And we use that to isolate any water, and that will drive the reaction towards the acetal. And so you might be wondering, or maybe you're not wondering, but maybe you are. What if I had a diol? Right? What if I used ethylene glycol? Right? Ethylene glycol, this molecule here, this is found in antifreeze. What if I took that and made a hemiacetal, then an acetal? I'd end up with a cyclic acetal, wouldn't I? The answer is absolutely you would. Yeah, absolutely. And we love to use cyclic acetals. Organic chemists are hung up on them. Why? Because they make great protecting groups. Remember protecting groups that we looked at in chapter 12? Well, what we can do is we can form the acetal from the glycol, and we can protect the carbonyl, and then we can remove it using just dilute acid and water. So the way we do it is to favor acetal formation. What we do is we remove water, right? And that will drive the reaction in this direction. But to make it go in the opposite direction, what we do is we add lots of water and we just have our acid catalyst. So if you remove the water, it's going to push it towards the acetal. If you put a bunch of water in, it's going to push it back towards the ketone. And again, what's the rationale for doing this? Well, it enables us to use an acetal as a protecting group for an aldehyde or a ketone. That's the whole point here. So it says, consider how the following synthesis could be accomplished. Here we have a ketone in our molecule, and then we also have an ester. Now somebody reduced just the ester to make a primary alcohol, and they left the ketone intact. Well, how would we do this? The thing is there a way we could protect just the ketone? Going back here, okay, this whole protection scheme, it only works only for aldehydes and ketones. It doesn't work for esters. And so could we protect the ketone as an acetal and then do the reduction of the ester using lithium aluminum hydride and then remove the acetal by adding water and aqueous acid? The answer is absolutely we can. So this is what we would do. Step one, we would protect the ketone as a cyclic acetal. So for that, we use ethylene glycol. Again, that's this little guy here, ethylene glycol. We use a catalytic amount of acid, and of course, we remove water. Oh, and if you're wondering, do you write that? Yes. Removal of H2O. And so then all we'd have to do is treat it with lithium aluminum hydride that would reduce the ester. And then the acid at the very end, that's going to protonate or do the workup for the reduction, but it's also going to remove the acetal at the same time. It's going to do both things. So it's kind of like a double whammy at the end, like a double-edged sword, okay, if you want to use that. All right, there we go. So let's move on from there. So a hemiacetal, if we go back to that whole idea of the hemiacetal, where it's like you have a carbon that has an alcohol and an ether on the same carbon. It says hemiacetals are actually really difficult to isolate, very, very difficult to isolate. There are some exceptions, though. There are some exceptions. A big exception to this, so it says cyclic hemiacetals can usually be isolated. The cyclic hemiacetals that would be of interest to us a lot of the times are carbohydrates. I'll just put here example, carbohydrates. So if you've studied biology and you've seen carbohydrates like this, if you've seen that form of glucose, that's a hemiacetal, believe it or not. So if you look at this carbon, we call that the anomeric carbon. It goes carbon, oxygen, carbon. So that's an ether here. And then here it goes carbon and then a hydroxyl. So that carbon is part of a hemiacetal in glucose. So that's when we see a hemiacetal as being stabled, is when you form a six-membered ring. So six-membered ring. And hopefully you remember in OChem, a six-membered ring is a very stable ring, right? We like six-membered rings as organic chemists. Well, with all that in mind, Let's see if we can draw a plausible mechanism for this doozy, okay? So we're going to take cyclopentanone and we're going to convert it into this dimethyl acetal. And remember, our acid that's going to do the protonation in the first step is going to be what? It's going to be the protonated form of methanol, right? This is our HA+. Okay, so we'll put in our carbonyl, and the first step is going to be a proton transfer to convert that carbonyl into a really powerful electrophile. So let's do that. Let's draw the oxonium. Going to look something like this, okay? And now, remember, there's always going to be an equilibrium. If I go, look, let me just write it down here. There's going to be an equilibrium, right? Because you've got methanol plus sulfuric acid, and there's an equilibrium between this, right, the protonated form of methanol and the hydrogen sulfate ion. So you're going to have both this and this present in the mixture, and it's going to go back and forth, right? It's going to donate a proton, then it's going to accept a proton, then it's going to donate a proton, accept a proton. So it's going to keep going back and forth. So in this step, you removed a proton from the protonated species. So now in the next step, you have methanol kicking around, right? So what's going to be the nucleophile here? It's going to be, do you want me to write Me or do you want me to write CH? I'll just use MEOH. This is going to be my nucleophile. So it's going to do a nucleophilic attack like this. And now we're getting very close to our hemiacetal, right? We're going to have this, plus we're going to have this oxygen that still has the proton on it. So we'll put Me plus like this. So now we're getting closer to our hemiacetal. So who's going to remove that proton to make the hemiacetal? Remember, you still have methanol in the reaction mixture. You've always got both of these things. And so the methanol is going to remove a proton like this. And there you go. Now you've made your hemiacetal. So here we go. We have the hydroxyl here, and we have the ether over here. So this is our hemiacetal. And so to get from here to here, what do we need to do? More steps, and we need to lose water because you lose water in the second step. So in order for us to lose this as water, we've got to protonate it, right? So we're going to do a proton transfer, and we're going to use our protonated form of methanol, which is going to be the most abundant acid in our reaction mixture. So we're going to do a proton transfer on that guy, and we end up with this. Now we've converted the hydroxyl into a good leaving group. Comme ça, as we say in French. All right, there we go. And this is a very important step. In order to lose that leaving group, let me draw these two electrons very clearly. We're going to restore the double bond, and we're going to lose the leaving group like that. Right, and there's a good reason for that, because now we have our carbonyl, which is a really powerful electrophile. So here's where we lost the water, right? The water is gone. And so now we have methanol coming in as a nucleophile to make our hemiacetal. So it's going to come in and attack here. We're going to end up with, I'll just draw it like this, OCH3, CH3, and this has a positive charge. Let me move this over here like that. And then to get to the very end, get to our product, who's going to take the proton? It's going to be another molecule of methanol, which is going to grab this proton. And there you go. And so now we've regenerated this in the very end, right? This is going to take on the proton to get us back here. And so that's why you only need a catalytic amount of acid, because it keeps getting recycled over and over and over. There you go. We go from our hemiacetal to our acetal. This is a mechanism that might seem intimidating, but it's one that all the organic chemists need to know. It's right up there with the most important mechanism in the world, which is Fischer esterification. And we haven't learned that yet. So what we'll do now is we'll take a short break, and then we're going to come back and we're going to see if we can propose, some synthesis ideas for these reactions here. And then after that, we'll take a look at nitrogen nucleophiles. So let me just see here, nitrogen nucleophiles. Hydrolysis of this. All right, so we'll come back and we'll take a look at these problems.